Good morning and welcome to this 9th edition of the Great Designs in Steel technical webinars. My name is Brian Esterberg and I'm the Senior Automotive Market Strategist at the American Iron and Steel Institute. Today's presentation will examine the effect of substrate composition on liquid metal embrittlement susceptibility in third-generation advanced high-strength steels. Before we get started, just a few reminders and housekeeping items. Save the date, May 20th, 2026. This May 20th for our annual Great Designs in Steel Symposium, once again taking place in Novi, Michigan. Our preliminary agenda and speaker announcement will be released very soon, along with opening of registration. Watch for that announcement in the weeks ahead. We hope to open registration by the end of January. The deadline for speaker abstracts is this week. If you'd like to submit an abstract, please do so right away through the Great Designs in Steel website. And for those interested, exhibiting sponsor opportunities are still available also at the Great Designs in Steel website. Stay tuned for our next GDIS technical webinar. That'll take place on February 24th. Please mark your calendars. That'll be considerations for design and stamping of Gen 3 steel grades, presented jointly by representatives from ArcelorMittal Global R&D and Kirchhoff Automotive North America. Details and registration will be announced soon and be available at autosteel.org. So as always, your microphones have been muted. Please use the Q&A feature in Zoom to submit questions. We won't be using the chat or raised hand feature today. Again, use the Q&A feature to submit questions for Jake following the presentation. My colleague, Dr. Hisham Izat, our Senior Technical Advisor, will join Jake to address your questions following the presentation. And as usual, a recording of today's presentation and the slides will be made available at autosteel.org following today's presentation. So with that, it's now my pleasure to welcome Jake Colburn, Ph.D. candidate at ASPPRC at the Colorado School of Mines. His presentation again is titled Effect of Substrate Composition on Liquid Metal Embrittlement Susceptibility in Third-Generation Advanced High-Strength Steels. Welcome, Jake. Good morning.
Good morning, Brian. Thank you for the introduction. All right.
You're good to go.
Sounds good. Thanks, Brian. So again, hello, everybody, and thank you for joining us again. As Brian mentioned, my name is Jake Colburn. I'm a PhD candidate at the Colorado School of Mines, working in the Advanced Steel Processing and Products Research Center, where I'm advised by Professors John Spear and Yona Klemtul. And again, today we'll be talking about the effect of substrate composition on liquid metal embrittlement susceptibility in third-generation advanced high-strength steels. And so to set up a little bit of the background, a little bit of why we are concerned with liquid metal embrittlement, we'll begin here by looking at our elongation versus tensile strength plot for a range of different first generation and second generation advanced high strength steels. And we see that as the automotive industry has been designed to create these lighter, stronger automotive bodies, that has begun pushing us into this area here up and to the right of the first generation advanced high strength steels, where we now have these third generation advanced high strength steels. And while this is no longer a future opportunity, this is where we have been moving with the creation of medium manganese steels, quench and partition steels, and TBS steels, to name a few. And so the idea here is that we're creating these steels with a greater combination of elongation, tensile strength than the first generation advanced high strength steels, while still maintaining lower alloying cost than our second generation advanced high strength steels. However, when these third generation advanced high strength steels are galvanized with a zinc coating and then joined via resistant spot welding for the production process, we see that cracks can form along the weld shoulder and weld periphery, most notably for these steels. And this cracking can lead to both the mechanical and aesthetic degradation of the welds, which can therefore then make it difficult as the automotive industry to be able to implement these steels in usage for automotive bodies. And so specifically for liquid metal embrittlement cracking that we saw with those cracks that form in the weld shoulder, we see that these cracks are always going to be coinciding with the presence of zinc from the galvanized coating. And so this is one of the things that is hinting us towards the fundamental idea that LME cracking, liquid metal embrittlement is cracking, is because as we see these cracks, we can also see the presence and penetration of zinc from the coating along with that. And so I've mentioned liquid metal embrittlement a couple of times, LME. So what specifically is LME? So here we have the triangle here where we see these three components that are necessary to create LME. So tensile stresses, a susceptible material, and aggressive liquid metal, those are the three components that are necessary concurrently to both initiate and propagate LME. And so with LME, we can then define that as the decrease in energy for grain boundary decohesion due to grain boundary penetration of a liquid embrittler. So essentially, a normally ductile material is going to behave in a brittle fashion. And that brittle behavior of the material is then what is going to lead to this crack formation that we see in these welds. And while there are a number of binary LME couples that we could be concerned with, the ones that we're going to be looking at for galvanized third generation advanced high strength steels is going to be the zinc iron LME couple. And so more specifically, as we look at each of the three of these components that leads to LME, we can begin by looking at what aggressive liquid metal are we concerned with in this system. And again, that's going to be liquid zinc that we have forming during the weld cycle as that temperature reaches above 420 degrees Celsius, and liquid zinc can then melt. And then as temperatures continue to rise, we can get penetration of the zinc into the substrate, as we see here with this zinc EDS map, where we see penetration of zinc into the substrate. So that's our aggressive liquid metal. For tensile stresses, we can have thermomechanical stresses that develop during the weld that can help be this second leg of the tensile stresses for our LME components. And so here on the right, we have a figure that shows some FEA simulations of a weld electrode here, welding these two workpieces. And then below that, we have the stress and temperature profiles for different locations, different nodes throughout this FEA simulation. So we can see that as the weld time progresses at different locations, we'll see different thermal profiles, different stress profiles, but generally we can see these rapid increases and decreases in temperature, as well as these tensile stresses that are going to develop during the weld cycle. And so as the substrate's heated during the weld cycle, we have that compression from the electrode, and then that rapid cooling is what can develop these thermomechanical stresses that are necessary for LME. And then as we look at our susceptible material, generally we're concerned with these higher strength, that being around or above 900 megapascal, steels with higher fractions of austenite and martensite, and also potentially bainite. And so for generally lower strength steels that also may have these larger fractions of ferrite, such as dual phase steels, we see that LME is generally less of a concern. We have less LME susceptibility generally with those steels. However, if we have steels, even in our first generation class, such as our martensitic steels, that contain large fractions of martensite, of retained austenite, and or bainite, such as our QNP and TBF, third generation advanced high strength steels, we see that these are steels that are more likely to exhibit LME and be susceptible materials for liquid zinc penetration and embrittlement. And so generally, as we think about how to tackle the problem of LME, how we can potentially mitigate or prevent LME, the idea is that if you can remove the presence of one of these factors, if we can remove a leg of this triangle during the weld process, then we should be able to mitigate or prevent LME, because again, we need the concurrent presence of those three factors. And so today we're going to be looking at how substrate composition is affecting LME susceptibility, and seeing specifically how that substrate composition can potentially either decrease or increase the susceptibility of the underlying substrate, as well as how composition in the substrate can potentially affect the presence of this aggressive liquid metal, of the liquid zinc. And so with that, we'll begin to take a look sort of at this example case where we'll take a look at the effect of substrate silicon and aluminum content in LME susceptibility for third gen advanced high strength steels. But first, we're just going to focus on silicon content and its effect on LME susceptibility. So here on the left, we have the composition of the two alloys that we're looking at. And as a third gen steel, quench and partition microstructure, we see our four main alloying elements of concern, that being silicon, aluminum, carbon, and manganese. And for these two alloys, we have equal compositions of aluminum, carbon, and manganese, and we're varying the silicon content from a relatively low level of 0.5 weight percent to a relatively higher level of 1.5 weight percent. And the reason that we have the addition of silicon and also aluminum is that those can act as carbide suppression during the quenching and partitioning process, and then also act as solid solution strengtheners. And so these two alloys, they were laboratory produced, hot rolled, cold rolled, and then went through continuous annealing simulations and then we're electrogalvanized with a pure zinc coating. And so if we take a look at the microstructures that we have for these two alloys, we see what we would expect again for a quenchum partition microstructure with relatively high fractions of martensite, some retained austenite present, but then also notably this higher fraction of cementite or carbides here in the lower silicon containing steel due to having that lower alloying presence of a carbide suppressor in this alloy. And so then as we begin looking at the LME testing, one of the first tests that we can do is hot tension testing, which is essentially a thermomechanical simulation of the resistant spot weld stress and thermal conditions. And of course, this is going to be a simplified condition of our stress and thermal states because many of the stress and thermal states that we have during resistance spot welding can be much more complicated than just the uniaxial tension that we're going to be applying during this test. But again, here we have our tensile specimen that will be rapidly heated up to our test temperature, held for a short amount of time, deformed to failure, and then rapidly quenched. And so this test temperature at which we choose to hold the material is going to be of importance for both the underlying substrate microstructure, but also it's important in terms of what iron, zinc, intermetallics we could potentially expect to be present upon deformation. And so here we have our iron zinc binary phase diagram, or if we look at the zinc-rich corner of the phase diagram, we see that in our general test temperatures for hot tension testing around 600 to 900 degrees Celsius, we have a range of different iron zinc intermetallics as well as the phase fraction of those iron zinc intermetallics and the liquid phase present depending upon what test temperature we'll be at and how much diffusion has occurred from the coating and how much zinc and iron is present at that point. And so as we take a look here at some of the results for the silicon effect on LME with our hot tension test results, here on the left we have these macrofractographs of the hot tension samples tested at three temperatures, 6, 7, and 800 degrees Celsius. And we have the high silicon containing steel on the left, low silicon containing steel on the right. And the main thing that we can see here is this relatively lower degree of necking in the high silicon containing advanced high strength steel, which is going to be indicative of a lower degree of ductility during testing. But then we can also do a little bit more of a quantitative look at the ductility loss when the sample is compared to its bare state versus its coated state, again, testing at that temperature of 700 degrees C. And so what we see here is that there is a greater ductility loss between the bare and zinc-coated steel for the high silicon containing steel as compared to the lower silicon containing steel at 700 degrees C. And overall, we can say that this 1.5 silicon advanced high strength steel showed a greater ductility loss, a greater degree of embrittlement than the lower silicon containing steel. And then if we want to take a look more deeply into potentially why we're seeing the differences in this behavior, we can start by looking at some of these SEM images of the cross-section of the hot tension samples after testing at 700 degrees C. And so here we have backscatter electron images to where the contrast is going to be related to the atomic number of the elements that we're looking at. And so zinc having the highest atomic number of the elements that we're looking at is going to appear with the lightest contrast. So when we have those regions of zinc that have alloyed some with iron, we're going to see a darker contrast. And that's what we see here on the right with our low silicon containing steel, where at the interface, we see the presence of this iron zinc intermetallic layer, specifically the gamma phase. And this gamma phase is important because its formation can consume the liquid zinc that is present, as well as act as a physical barrier to further zinc penetration. So we see at elevated temperatures at our test temperature, if this continuous physical layer of the gamma is present and we have liquid zinc above, that's going to create a barrier to the liquid zinc further penetrating the substrate, whereas with the high silicon containing steel, we don't see the presence of that intermetallic layer, and we're readily able to get zinc penetration into the substrate because there's no inhibition of the zinc into the substrate. And then if we zoom in a little bit and take a look at a TEM lift out of the interface of that high silicon containing cross-section of the hot tension sample. So here we have a STEM EDS line scan. So this is scanning transmission electron microscopy, energy dispersive spectroscopy scan through here to where we see the composition of this line as we move from the top of this region of the coating into the substrate. And of noticeable concern here, we see when we look at the silicon concentration across this line, we see a noticeable enrichment of silicon at the interface that is above that of the bulk composition. So again, if our bulk composition is around 1.5 weight percent, we see an increase of that up to roughly 3 to 4 weight percent at the interface. But we also see the presence of these silicon-rich alpha iron zinc islands. And so this alpha iron zinc phase is essentially a BCC iron phase that has appreciable solubility for zinc, as well as also having a decent solubility for the silicon phase. And so we see these little islands here pointed out by C and B over here of this alpha phase. And so again, for the high silicon containing steel tested at 700 degrees C, we see this silicon enrichment at the interface as well as the presence of these iron alpha zinc phases. And so if we want to understand a little bit more about potentially why we're seeing this the difference in behavior, difference in ductility, the silicon enrichment, we can begin by doing some thermodynamic and diffusion modeling. And so here on the left, we have a diffusion couple of liquid zinc on the left side, silicon-containing iron on the right side. And this is a diffusion calculation up to 0.5 seconds. And so we see that as time progresses, there is silicon enrichment at the interface. And so as the liquid zinc dissolves the substrate, the silicon has very low solubility in the liquid phase as compared to the iron in the steel. And so the iron is able to be dissolved into the liquid, whereas the silicon will accumulate or enrich at the interface as that interface is moving in towards the substrate. And so if we're having a change in the local composition at the interface, if we're increasing the composition and the content of silicon at the interface, we'd expect that that can potentially affect what phases are stable, what phases can form, and the fractions of those phases at the interface. And so that's where, if we look here at the zinc and iron-rich corners of the zinc, iron, silicon ternary phase diagram, we can pick a composition ratio of iron and zinc that we see at the interface, and then begin to add silicon while maintaining that iron to zinc ratio at the interface. And so from that, we can then calculate what the fraction of phases that we expect to be formed there. So this is the equilibrium volume fraction of each of these phases at 700 degrees C for increasing silicon concentration. So here we're adding silicon to the local composition at the interface. And what we see is that as the silicon concentration increases at the interface, we have a decrease in the equilibrium phase fraction of the gamma phase, and then an increase in the equilibrium phase fractions of the liquid and the alpha iron zinc phases. And so that's important because if we're increasing the phase fraction, if we're further stabilizing the liquid phase, that is going to be detrimental to LME susceptibility because this is the phase that is necessary to initiate and propagate LME. But if we're also stabilizing the alpha iron zinc phase instead of the gamma phase, we're stabilizing a phase that, especially in these lower volume fractions, is likely to form in a globular morphology. So as those small islands that we saw in the stem image, this is what we see here generally with the alpha iron zinc phase. And so we could say that as we're increasing the silicon concentration in the substrate and then getting enrichment at the interface, we are going to have a detrimental situation for LME susceptibility by inhibiting the reaction of forming the gamma phase, but then also stabilizing these two potentially detrimental phases for LME susceptibility. And so if we put most of those results together, we can see that the higher silicon-containing steel exhibited this higher LME susceptibility than the lower silicon-containing advanced high-strength steel. And we can attribute much of that to saying that if there's an increasing silicon content at the interface, we saw silicon enrichment present at the interface that also then led to suppression of the iron-zinc intermetallic reaction, specifically that gamma phase. And overall, that then leads to increased liquid fractions or increased liquid availability at the interface and therefore increased LME susceptibility. And so now we're going to take a look. So that's specifically looking at silicon, but then now we can take a look at the effect of aluminum content on LME susceptibility. And so the main reason we want to do that is that, again, as an alloying addition, if we say that we want to keep the silicon concentration lower so as to not increase the LME susceptibility, we can then substitute some of that carbide suppression and solid solution strengthening effect of silicon with aluminum. And so here again, we have two alloys that we're going to be comparing that have equal compositions of silicon, carbon, and manganese, and we're changing the aluminum concentration from our low value at 0.05 weight percent to the high aluminum alloy, which is 1.38 weight percent aluminum. And so these two alloys were also produced in the same way as the previous ones, and they were laboratory produced, hot rolled, cold rolled, went through continuous annealing simulations, and then were electrogalvanized with a pure zinc coating. So again, if we take a look at the microstructures of these two alloys, what we see is, again, what we expect for a quench and partition microstructure of having a relatively high volume, fractions of martensite, having some retained austenite. But then notably for our higher aluminum alloy, we see still some ferrite present. So this darker contrast region here, we would identify as ferrite, also up here in the top of the micrograph. And so due to the higher AC3 temperature of the high aluminum alloy, likely full austenitization was not achieved during the continuous annealing simulation. So there's potentially some ferrite still present near the surface of this alloy. And so then if we take a look again at our hot tension test results and take a look at our macrofractor graphs here, taking a look at the low aluminum alloy at the top, the high aluminum alloy at the bottom, tested at 800 degrees C, we see a greater reduced area, slightly greater reduced area, indicative of a greater ductility present at elevated temperatures for the high aluminum alloy, as well as more of this secondary cracking appearing in the high aluminum alloy, which are these small cracks that we see appearing on the surface, that we see more so in the high aluminum alloy as compared to the low aluminum alloy, where a majority of these cracks seen on the surface are just cracks in the solidified coating layer. And so, again, this testing was done at 800 degrees C, which is a notable temperature because we're now above the paratectic temperature for the gamma phase. So in the binary iron zinc system, we would expect that the gamma phase is not going to be stable at this test temperature. And so if we compare the ductility losses between the bare and coated samples of these two alloys during the hot tension test from the stress strain curves, we see a lower ductility loss for the higher aluminum alloy to a lower extent than what we saw when comparing our high and low silicon alloys, but still a noticeable difference in the ductility loss between these two alloys. And so we would say that the higher aluminum alloy exhibited lower ductility loss, a lower degree of embrittlement in this test. So then if we again start by looking at the backscatter electron images of the crack tips of a LME crack for the low aluminum sample here at the top, the high aluminum alloy here at the bottom. Notably, what we see here is that there is this greater degree of zinc enrichment penetration in the low aluminum alloy when compared to the high aluminum alloy. So this contrast here, this lighter contrast is again going to be indicative of higher levels of zinc in that area, and this was confirmed with the EDS. But that higher contrast region is not really seen as much with our high aluminum alloy as compared to the low aluminum alloy. And this is potentially indicative of the relative amount or availability of zinc during testing here, potentially having higher levels of that zinc availability in the low aluminum alloy as compared to the high aluminum alloy. And again, if we want to try and understand somewhat how the aluminum in the substrate is potentially affecting what phases are present at the interface and affects that local composition, we can start again by looking at our diffusion couple, again, of liquid zinc here on the left, a aluminum silicon containing iron phase on the right. And we see that after simulating at 800 degrees C for 1 second, we again, like silicon, see this potential enrichment of aluminum at the interface due to the low solubility of aluminum in the liquid phase as compared to iron. So again, if we expect a change in that local composition at the interface, we can expect that there will potentially be a change in what phases are present in the equilibrium fraction of those phases present at the interface. And so again, like before with silicon, we can calculate the phase volume fraction versus the aluminum concentration at the interface. And rather than seeing that monotonic behavior that we saw with silicon, where increasing silicon content decrease the gamma phase stability across all the compositions. Here we see that there is an intermediate range of aluminum concentration at which the gamma phase has a higher volume fraction stable than the liquid phase. So we see here that as we add aluminum up to about 3 weight percent aluminum, the liquid phase is destabilized and the gamma phase is further stabilized. But then if we're concerned about that composition, that if we go higher than that, we then begin to stabilize the liquid phase in the alpha iron phase. But if we look at what our bulk composition is at starting at 1.38 weight percent and then potentially enriching in that 2 to 4 weight percent range, we're still in this orange box here of our composition where we have much higher volume fractions, equilibrium volume fractions of gamma phase stable as compared to the liquid phase. So we would expect that with that interfacial composition that the gamma phase would be stable. And so we would say that that is potentially going to be beneficial for LME susceptibility, again, decreasing that the availability and presence of the liquid phase at the expense of by having more of the gamma phase present. But then we can also take a look at how the change in the substrate aluminum concentration is going to affect the diffusion of zinc into the substrate or affect the solubility of zinc in the substrate. And so here we have calculated the mass fraction of zinc in those substrate phases at 800 degrees C for increasing aluminum concentration at different zinc concentrations in the substrate. And the main trend that we see here is that as we increase the aluminum concentration in the substrate or at that interface, what we see is a decrease in the mass fraction of zinc in the substrate, or essentially what the maximum solubility of zinc in the substrate would be. We see a decrease with increasing aluminum content. But even more than that, we see that increasing aluminum concentration in the substrate also affects the diffusivity of zinc in the substrate, to where as we increase the aluminum concentration again at different zinc contents in the substrate, we see the diffusion coefficient of zinc generally decreases. And so we could say that there is a general decrease in the diffusivity of zinc in the substrate with increasing aluminum content. And so with those two factors, if we're concerned with the flux of zinc, if we're concerned with the diffusion flow of zinc into the substrate, that's where we can go back to Fick's first law here, where we say that the flux of the diffusion component into another component is going to be equal to the product of the diffusivity of that diffusing component and the concentration gradient of that diffusing component. And so again, those are essentially two of the factors that we just saw calculations for, to where specifically, if we're interested in looking at this composition or concentration gradient, we can take a look at the schematic here on the right, where we have our high-containing liquid zinc on the left side, our substrate on the right side, which initially is going to have 0 zinc into it and going to have regions of 0 zinc concentration. And so here at the interface, we're showing that if we're changing the maximum solubility, if we're changing the equilibrium concentration of zinc in the substrate by adding aluminum, we're going to be changing the concentration gradient into the substrate. So we see that moving from a low aluminum concentration here in point A to a high aluminum concentration in the substrate in point B is going to, again, decrease the equilibrium fraction of zinc, the maximum solubility of zinc in the substrate, such that as we then move a distance into the substrate where there is no zinc, that concentration gradient is going to be decreased. So we see that increasing the aluminum concentration is going to, should decrease, potentially decrease the flux of zinc in the substrate by both of these factors here, by decreasing both the diffusivity of zinc and that concentration gradient of zinc into the substrate. And so if we take some of those points together here with a quick sub-summary, we see that the higher aluminum alloy, we saw lower LME susceptibility and zinc penetration and enrichment to our low aluminum alloy. And from those thermodynamic and diffusion calculations, we predicted potential aluminum enrichment at the interface, a decrease in the equilibrium mass fraction and diffusivity of zinc in the substrate, and then again, the stabilization of this beneficial gamma phase at the expense of a detrimental liquid phase with increasing aluminum at the interface, again, up to roughly 3 weight percent aluminum. And above that, then the liquid phase begins to be stabilized to a greater degree again. So then with that, the idea was the next step we wanted was saying, okay, if from those conclusions, those results we saw in hot tension testing, will we see similar results in resistant spot weld testing? So the LME testing that we did in resistant spot welding consisted of creating a single square pulse weld at an increasing current through the 6 to 9.5 kiloamp range in 0.5 kiloamp increments with a weld time of 600 milliseconds, which is roughly twice that of what the standard would be for this sheet thickness. And we did that to ensure that there's adequate heat input to initiate LME at each of the weld conditions that we used. And so the LME metric that we're interested in using here is the crack index, which is going to be the product of the number of the cracks in the log normal median crack length for a given sheet thickness. And so we see that a higher crack index is going to be indicative of a higher LME susceptibility because there's either a greater number of cracks and or a greater average length of those LME cracks. And so here's the figure on the left. We're comparing the average crack index of these two alloys at different weld currents relative to the expulsion current. And we're comparing relative to the expulsion current to try and compare these welds at relatively equal heat inputs because these two alloys are going to have different expulsion currents due to the higher alloying addition in the high aluminum alloy. But we see here that the higher aluminum alloy exhibited a lower crack index or lower LME susceptibility at each of these current levels, except for one in which at the 0.5 kiloamp condition, we see relatively equal LME susceptibilities or crack indexes for the two alloys. And then if we're interested in taking a look at the cross-section of these welds, and so here we have the low aluminum alloy welded at 1 kiloamp below and above its expulsion current. And we see here a cross-section of the weld with the weld shoulder and weld periphery, these optical micrographs where the substrate was etched with 2% nitrile. And so what we see here is that even 350 microns into the weld periphery, what we still see is what we could describe as the supercritical heat affected zone in this region, to where the microstructure is a mostly martensitic microstructure with potentially still some bainite, this lower current. But this would indicate, if this is a supercritical heat affected zone, that at the peak temperature of the weld, that this region was likely fully austenitic, and then as the weld current stopped and the substrate was rapidly cooled, then we get this transformation to martensite and or bainite present. But then when we compare that to the high aluminum alloy, and here again looking at the optimal micrographs of the high aluminum alloy welded at 1 kiloamp below and above the expulsion current, we see that at the weld shoulder, we see that there's still noticeable amounts of ferrite present in the microstructure. And so we can then describe this as being part of the intercritical heat affected zone in the weld periphery. And so at the peak temperature of the weld, we would expect that potentially this region was austenite plus ferrite as well, and that there wasn't full austenitization of this region at the peak temperature, and so that ferrite remains stable upon quenching. And so as we take a look at the transformation temperatures, we see that this trend begins to somewhat make sense as we compare the AC1 and AC3 temperatures for these two alloys, where the AC1 temperature, so that being the temperature upon heating, which we enter the austenite plus ferrite two-phase region, we see roughly equal values there, 740 degrees C for the two alloys. But then as we look at the AC3 temperature, so that's the temperature heating from the austenite plus ferrite two-phase region into the single-phase austenite region, we see an increase of roughly 120 degrees Celsius for the high aluminum alloy, which is then also going to increase the width of that intercritical transformation temperature range, that being the difference between those two transformation temperatures. And so if we again go and look back at the high aluminum and low aluminum optical micrographs of these welds, what we see is again indicative of these transformation temperatures, where we see a smaller intercritical heat affected zone width for the high aluminum alloy of both of those currents as compared to this wider intercritical region that we see for the high aluminum alloy, where there's still ferrite present in these regions. And then if we take a look at the supercritical heat affected zone, we see that that region extends to much greater distances into the weld periphery for the low aluminum alloy than we see for the high aluminum alloy, where potentially this supercritical heat affected zone is not extending at all into the weld shoulder and the weld periphery. And so then the question is, why does it matter if we have a intercritical or a supercritical heat affected zone at these LME susceptible regions? And for that, we can begin to take a look at the secondary electron and EDS SEM images of the weld shoulder for the low aluminum and high aluminum alloy welded at half a kiloamp above the expulsion current. And what we see here for the low aluminum alloy is, again, what we'd expect for a supercritical microstructure where we have mostly martensite with these LME cracks propagating, presumably along the prior austenite grain boundaries. Whereas with the high aluminum alloy, we see still noticeable amounts of ferrite, those being these darker contrast regions. And we don't have a distinguishable crack propagation path through this microstructure. But more than that, we also see that there's a difference in the zinc penetration and enrichment between these two alloys, where in the low aluminum alloy, we have, again, this noticeable zinc penetration and enrichment along and ahead of these LME cracks at the shoulder, whereas with the high aluminum alloy, there's really no noticeable zinc enrichment or penetration that we can detect here in EDS with the scan, to where any of this zinc contrast that we see here is just going to be background noise that's due to a difference in the counts per second that we're getting between the substrate and the mounting material here. But even more than just affecting potentially the zinc enrichment penetration behavior, changing whether we have an intercritical or supercritical microstructure at these LME susceptible regions can potentially affect the crack propagation path, to where again, at peak temperatures, we expect the supercritical heat affected zone to be the single phase austenite, so we can get zinc enrichment penetration along those prior austenite grain boundaries more easily than in the intercritical microstructure, where we have austenite plus ferrite at the peak of temperatures. And we can even see here with these small cracks formed that are roughly 10 or less microns, to where there's potentially some crack resting here due to not having sufficient zinc penetration into the substrate. So at the austenite plus ferrite, we can have this finer effective microstructure peak temperature, as well as potentially also this more tortuous crack path that's going to make it more difficult for these cracks to propagate and grow. And so putting, again, some of those conclusions together, we see that the high aluminum alloy exhibit a lower crack index during spot welding testing than the low aluminum alloy. And this high aluminum alloy, we saw an intercritical HAZ in the weld periphery as compared to that supercritical. For the low aluminum alloy, we saw less zinc enrichment and penetration for the high aluminum alloy, and a finer effective microstructure in the weld shoulder and periphery for the high aluminum alloy. And so with that, we then want to see if we can take some of those conclusions, some of those factors that we've seen when understanding the effect of silicon and aluminum susceptibility on liquid metal embrittlement, and see if we can potentially take some factors that could be applied to any alloying addition that may be of concern with an advanced high-strength steel. And so with that, we can then, I think, begin by asking 3 questions of how an alloying addition is going to affect the LME susceptibility for a material. So the first is asking how the alloying addition is going to affect the stability of iron, zinc, and metallics versus the liquid phase. Then how that alloying addition is going to affect the substrate microstructure at elevated temperatures, and then how the alloying addition is going to affect zinc diffusion and penetration. So then going a little bit deeper in each of those 3 questions, again, with the first, the stabilization of iron, zinc, and metallics versus the liquid phase, we can again go back to what we were looking at earlier of how aluminum and silicon concentration increase in that the interface affects the equilibrium phase fraction of our phases of interest that are stable there. And we can then begin to say, with that alloying addition, if we're stabilized in the liquid phase, we're then going to increase the availability of liquid zinc while decreasing the potential for forming this barrier to zinc penetration. Whereas instead, if that alloying addition is going to increase the phase fraction of iron, zinc, and metallics, and again, most notably the gamma phase, then we would have a potential decrease in the availability of liquid zinc, as well as a potential increase in forming that barrier to zinc penetration. So we see, again, increasing liquid fractions being detrimental for LME susceptibility, increasing the iron, zinc, and metallic phase fractions being positive for LME susceptibility. And then if we go to the substrate microstructure, again, comparing this supercritical HAZ to an intercritical HAZ, to where the microstructure that is present there is going to affect the effective microstructure size. So here's saying, how does that alloying addition affect the effective microstructure size? Again, are we potentially having single phase, 2-phase microstructure present at elevated temperatures? And then what is the fraction of those more susceptible phases potentially at elevated temperatures? as well as also the location of that. So whether we have an intercritical or supercritical AHSS or potentially some other type of heat effective zone or microstructure at those susceptible locations of the well is important. So we would be interested in knowing how that aluminum addition is going to affect for a given weld parameter, what the microstructure would be at the weld shoulder and weld periphery. And then taking a look at zinc diffusion and penetration. Again, the main question that we could ask here is, how does that alloying addition increase or decrease the thermodynamic propensity and driving force for zinc penetration and diffusion? So basically, as we add that alloying element, are we going to increase or decrease the driving force for zinc to diffuse and penetrate into the substrate, that being, again, detrimental to LME susceptibility? And the considerations there that we can look at are, again, two of the ones that we looked at today, looking at the solubility and diffusivity of zinc in the substrate, but then also even more fundamentally, looking at the driving force for diffusion being the chemical potential difference between zinc and the liquid and then zinc and the substrate, and how that alloying addition plays into that chemical potential difference, even how that alloying addition, when the substrate is under stress, is going to affect the chemical potential difference there and the overall driving force of zinc diffusion. And so with that, I'll wrap up with some quick acknowledgments here to our ASPPRC sponsors and mentors for the funding of this project, the providing the material as well as project guidance for the project, and then the University of Alabama College of Engineering and MTU department for access and assistance with their Global 3500 for hot tension testing, and then the Cleveland Cliffs Research and Innovation Center for access and assistance to using their resistance spot welding equipment. And so if you have any other questions or would like to contact me, there's my email at the bottom. And with that, I will hand it back over to Brian.
Hey, thanks, Jim. I'm going to look here at a list of the questions. I think you wrapped up the presentation very well. The last couple of slides kind of summarized everything that you kind of went through. Great work. I think you have a real big fan out there. My esteemed colleague, Dr. Michael Karagoulis, who's one of the outright experts on welding in the industry. He's really praising your work. So he had a couple of comments. One of them is that he has seen in isolated cases where copper from the electrode is found in the LME cracks, and he sees this element isn't on your list of embrittlers. So he's kind of like encouraging you to take a look at the effect. Copper is always present during spot welding, obviously through the weld tips. What do you think about that?
Yeah, I think that's interesting. And I would say, yes, I have seen some of that copper alloying in some of the welds that we've looked at. And again, yes, that would be great to look at. But then again, for simplicity and trying to just focus in on some of the main factors that we're looking at here, just trying to say that potentially that copper effect may be equal across those composition ranges when comparing the high silicon, low silicon alloy, and then the high aluminum and low aluminum alloy. We would say that maybe that's a constant across those two, and hopefully there's not too much of a difference between the behavior there. But I think we have had a student at Mines that's been looking at the effect of copper content on weldability, at least in terms of resistance spot welding when looking at residual copper. And so I think he also saw a negative impact of having increasing copper content in the substrate, at least, for resistance spot weldability. And so, but yeah, that's an interesting consideration to look at.
Okay. He also has another comment, and this is basically just a comment. It says, for future work, I suggest you focus on reducing cracks mainly at the structurally sensitive locations, which is the periphery. Getting rid of these cracks will increase market acceptability of these steels. So it's just basically the location of the cracking that occurs during that. So that's just a comment on his behalf. We do have another question. Thank you for a nice presentation. What are your predictions for the effect of bath aluminum, not just the substrate aluminum. For example, 0.2% aluminum GI bath on the results?
Yeah, that's an interesting question, and I think what we've seen, at least in the literature so far with that, is if you're increasing the aluminum content in the bath, at least by small amounts, again, staying within that hot dip galvanized range, that you could potentially see an increase in the thickness of the iron aluminide inhibition layer, to where potentially it's going to have a greater thermomechanical stability, to where you can potentially have a decrease in the LME susceptibility with an increase in that aluminum bath composition by increasing the thickness and stability of that iron aluminide inhibition layer. That makes sense to what I would think, and so I think that's what I would say in terms of that. We haven't really looked at that. We will be taking and are currently taking a look at basically comparing a hot dip galvanized to a galvannealed coating on LME susceptibility for a substrate with equal contents. And so I think it'll be a similar point there, to where if you can increase the stability of any of those intermetallic phases in the coating, and then again require higher temperatures, higher stresses to break down that inhibition layer, you can have a decrease in the LME susceptibility.
Okay. And on a related comment that I think you kind of covered it a little bit, it says this is an EG, this is electrogalvanized coated substrate. If it were GI, there would be higher aluminum at the intermetallic as an FeAl layer. Do you anticipate iron aluminum layer to have any effect on LME?
That's again a good question, and I think it would depend on the extent to which the aluminum in that intermetallic is actually diffusing into the zinc present in the coating. So when you have the liquid zinc in contact with the iron aluminide inhibition layer, how much of that aluminum is actually being dissolved into the liquid zinc? And for that, I'm not quite sure, because again, that intermetallic phase is going to have a much higher melting point than the pure zinc above it in the coating. And so if you do have a noticeable diffusion of aluminum into the melted zinc coating, then I think potentially you could have a decrease in the LME susceptibility. But it's also potential that if it's just under stress, that the inhibition layer breaks down, and then you're just creating pathways for the liquid zinc to penetrate in the substrate, and potentially doesn't have as much of effect, other than potentially just decreasing the overall availability of liquid zinc, as compared to just an EG coating where there's no inhibition layer that needs to be broken down in any way.
Okay. I think this is the last one that I have on the list. It says, thanks for the great work and presentation. What is the maximum LME crack length after resistant spot welding of the optimum steel alloy, the 0.5% silicon, 1.83% aluminum?
The maximum crack length that we saw?
It says, maximum LME crack length.
I think we saw cracks up to I think around 500 microns for that alloy. So still some noticeable LME susceptibility. Again, it's not a zero LME susceptibility alloy. And I think, again, part of that is also still related to using that higher weld time than, again, what would be standard for that sheet thickness of 1.5 millimeters. And so I think potentially if you're at a lower weld time, you could decrease that crack length some.
Okay. Very good. These are all the questions I have.
Okay.
So I would encourage, oh, wait a minute. We do have one more. Let me see. Have you studied the surface oxides on the steel surfaces, that it was different if it were annealed in a CGI? Not quite clear on what that is, but
yeah, that's a also a good question. And no, we haven't really taken a look into how the differences in the oxide, or even the extent of internal or external oxidation on these two alloys plays into the LME susceptibility. I think that would be a good part of the future work for this project. Again, I'm hopefully wrapping up here in a couple months, and so it's probably something that we won't get to, but I think would be definitely interesting to look at.
That's okay. That's great. So I would encourage, if you have any further questions, clearly, please contact Jake directly. His email address is on the last slide. Jake, this was a great presentation, very good detail. I think a
Thank you.
lot of great information. I know you're wrapping up in a couple of months, so I wish you the best in your future endeavors.
Thank
And
you.
hopefully we'll cross paths again in the near future.
Yes,
Okay.
sir.
Thanks, Jake.
Yes, thank you, Jim.
Back to Brian.
Jake, thank you very much for the presentation. Really, really impressive work, and thanks for joining us and sharing today. And Hisham, as always, thank you for facilitating the discussion. Thanks to everyone who joined us today. We appreciate you coming back and attending the webinar with us today. As always, the presentations will be made available through the autosteel.org website, recording of today's presentation, as well as the slides, which you'll find on our searchable database. Again, if your questions didn't get addressed, Jake's email address was there on the slides. Feel free to reach out to he or us for any further guidance. And just a quick reminder to save the date. Our next webinar has not yet been announced, but we will have it open for registration shortly. That'll be February 24th. That's considerations for design and stamping of Generation 3 steel grades, presented jointly by representatives of ArcelorMittal Global R&D and Kirchhoff Automotive North America. We'll also be opening registration for Great Designs in Steel, May 20th. 2026. That'll take place in Novi, Michigan. We expect to announce our initial agenda, speakers, and open registration before the end of this month. Thank you again all for joining, and make it a great day.